Hello, class. We switch topics now. We've been looking at the vapor power cycle, which uses a working fluid that experiences a phase change from liquid to vapor. And now we're going to switch to cycles that are based on a single phase, just a gas or a superheated vapor. And just like we did with the Rankine cycle, we're going to start with the most idealistic case, the Carnot cycle, and then we're going to proceed towards cycles that represent more reality. So let's start with a ideal gas power cycle, the Carnot gas power cycle. This is review material. All we're doing is we're using gas as our working fluid. It's still a Carnot cycle. So at this point we should understand that it has to have two heat transfer processes, and those have to occur ideally at a constant temperature. So in this example, process 2 to 3 is our heat transfer process from our hot reservoir. On the TH diagram, it looks like a horizontal line, constant temperature. And on a PV diagram, the process follows the isotherm that represents that high temperature. On the schematic here, we intuitively, hopefully can understand that as heat transfer occurs to the air, the working fluid, as an ideal gas, the gas is going to want to expand. And so conceptually, we'd have to allow that to expand to keep it at the same temperature. Isothermal expansion. Okay, the other heat transfer state is the heat transfer process is 4 to 1, and that is our heat rejection to the atmosphere of the surroundings. So on a TS diagram, that would look like the horizontal line at a constant cooler temperature. On a PV diagram, that looks like a line following the isotherm from 4 to 1. And we have heat transfer out, and conceptually we should understand that the air would want to cool and compress, and so we'd have to allow it to freely do that to keep it at a constant temperature. So the ideal conceptual process would look like a piston cylinder assembly. Okay, the Carnot cycle has the two constant temperature heat transfer processes. It also has the two isentropic or adiabatic and reversible work processes. So that would look like process 1 to 2 being the adiabatic, meaning no heat transfer, compression. Reversible, no heat transfer, that means it's constant entropy. And so that would look like a vertical line on our TS diagram from state 1 to 2. And then process 3 to 4 would be our adiabatic and reversible expansion process. Work out. On the TS diagram, that would look like a vertical line from state 3 to 4. So we've got our diagrams here, and this is a control system, right? So we should be able to understand that the net reversible work performed is going to be equal to the integral of the pressure with volume. And actually this is specific volume, so I guess I should technically write that as specific work. So the area under the curve here for the PV diagram would give me my net work performed by the ideal cycle. And then the TS diagram, likewise, would give me my net heat transfer. And since this is a cycle, through the first law of thermodynamics on the cycle, begins and ends at the same state, and I know that these two areas should be equal. The net work should equal the net heat transfer. And again, all of the previous things we discussed with the Rankine cycle for the Carnot cycle apply here as well. The thermal efficiency for any cycle is defined as what you want, the net work divided by what you have to pay for, the net heat transfer. The first law of thermodynamics on the control system as a cycle, I know that the net work equal to the net heat transfer. Again, that's just the first law on my control system for a cycle. And then the Carnot cycle establishes my ideal limitation, and it's based on the temperatures at which heat transfer occurs. And just a reminder, I'm not saying that temperature equals heat transfer. That doesn't make any logical sense. What I'm saying is the ratio of the heat transfers from the reservoirs is equal to the ratio of the absolute temperatures of the reservoirs for the Carnot cycle. And that establishes our upper limit of performance.